Today, we'll dive into shortest job first, SJF, scheduling. We'll explore its types, how it optimizes CPU usage, and the advantages and challenges it presents in managing process execution. Shortest job first, SJF, is a CPU scheduling algorithm that selects the process with the shortest burst time for execution next. It aims to minimize average waiting time, offering optimal performance in terms of this metric. However, SJF can lead to starvation for longer processes, as shorter ones keep getting prioritized. Shortest job first, SJF, is a non-preemptive CPU scheduling algorithm used in operating systems. It works by selecting the process with the smallest burst time, or CPU execution time, to execute next. The goal of SJF is to minimize the average waiting time of processes. Though it performs well in terms of efficiency, it has a downside. It can cause starvation, where longer processes might never get executed if shorter ones keep arriving. In CPU scheduling, shortest job first, SJF, has two main types, preemptive and non-preemptive. Non-preemptive SJF. Once a process starts executing, it runs to completion without interruption. The process with the shortest burst time is selected next. While efficient in terms of minimizing waiting time, it can cause starvation for longer processes. Preemptive SJF, shortest remaining time first, SRTF, in this version. If a new process arrives with a shorter burst time than the currently running process, it preempts the current process. This allows for more dynamic scheduling, but adds complexity to process management. Types of SJF in OS, non-preemptive SJF. Once a process starts executing, it runs to completion. The CPU is assigned to the process with the shortest burst time, may cause starvation for longer processes. Preemptive SJF, shortest remaining time first, SRTF. The currently running process can be preempted if a new process with a shorter burst time arrives. More dynamic but adds complexity in managing context switches. Both aim to minimize average waiting time but differ in how they handle interruptions. Welcome to this quick guide on the shortest job first, SJF, scheduling algorithm. Let's take an example. We have for processes P1, P2, P3, and P4, with their arrival and burst times. Process details: P1 arrives at 0.0, burst time 7. P2 arrives at 2.0, burst time 4. P3 arrives at 4.0, burst time 1. P4 arrives at 5.0, burst time 4. In SJF, non-preemptive, the process with the shortest burst time is scheduled first. Gantt chart: P1, P3, P2, P4. Final times: average time, for ms. Average turnaround time, 8 ms. Estimating the next CPU burst in shortest job first, SJF, scheduling is challenging because future burst times are unknown. However, we can make predictions using exponential averaging. The formula is +1 equals +1 tau, n plus 1, where t is the actual burst time, tau is the predicted burst, and alpha is a weighting factor between 0 and 1. A higher alpha gives more importance to recent bursts, while a lower alpha considers past bursts more. Equals alpha Tn plus 1 alpha tau n, where t is the actual burst time, tau is the predicted burst, and alpha is a weighting factor between 0 and 1. A high alpha gives more importance to recent bursts, while a lower alpha considers past bursts more. Shortest job first, SJF, scheduling is one of the most efficient CPU scheduling algorithms. Let's explore its advantages. Minimizes average waiting time. Since shorter processes execute first, the overall waiting time is reduced, making it more efficient than first come, first served, FCFS. Improved turnaround time. By prioritizing shorter jobs, processes complete faster, leading to better system performance. Higher CPU utilization. SJF keeps the CPU busy with short tasks, reducing idle time and maximizing efficiency. However, predicting burst times is tricky. Despite this, SJF is widely used where predictions improve system responsiveness. While shortest job first, SJF, scheduling is efficient, it comes with several drawbacks. Let's explore the key disadvantages. Difficult to predict CPU burst time. SJF requires knowing the burst time of each process in advance, which is often impractical in real-world systems. Starvation of long processes. Since shorter jobs prioritize, longer processes may experience indefinite delays, leading to starvation in cases of continuous short job arrivals. High overhead in preemptive SJF. In preemptive SJF, shortest remaining time first, S or TF. Continuous tracking and reordering of processes increase scheduling overhead. Not ideal for tiring systems. SJF lacks fairness in interactive environments, where response time is crucial for user experience. Despite these challenges, SJF remains useful in batch processing, where job lengths are predictable. To summarize, SJF minimizes average waiting time but may lead to starvation. Thank you.